This video is about the characteristics of quadratic functions. So we've been studying some quadratic functions for a few days now, and hopefully you've noticed some characteristics already. This is going to be a little bit of an overview, which hopefully is a review for many of you, but might not be. So we're going to look at the characteristics of quadratic functions, quadratic growth, so we can really be able to tell the difference between whether something can be modeled by a quadratic function as opposed to a linear or exponential function, or maybe even some other function that we haven't even studied. So first, let's look at the definition of a quadratic function. So a quadratic function is a function that has only non-negative whole number exponents for the variable and whose highest exponent is 2. So another way of saying that is that it's a polynomial of degree 2. We haven't learned about polynomials yet. Degree just means the highest power for the variable. So the highest power is 2. So here are some examples of quadratic functions and non-quadratic. So this first one here, we can look and see it has x to the second power. So it has the highest power, highest exponent is 2. It's quadratic. This one also has an exponent of 2 as its highest exponent to the variable, 3x squared minus 2. Over here, well, I don't see any x squared or t squared, but if we were to multiply this through using the distributive property, we'd see t times t is t squared. So yes, this in fact is quadratic, because if you simplify the expression over here, you will get t squared and see that 2 is still our highest power. This one here, m of x is negative 6.2x squared plus 4.1x minus 2. Well, here I have decimals, I have negatives. This said something about non-negative, whole number, but it's just for the exponents. So here, we're fine with a coefficient being negative or a decimal. The definition says nothing about coefficients. It only says something about the highest exponent and all the exponents. So let's look over here at some non-quadratics. Hopefully you recognize this right away as a line. Highest exponent here is 1, right? X to the first power is x. Over here we have something that's cubic. It's x to the third power. Too big. Here, this looks good. We have x squared, x to the second power. But over here we have not a whole number exponent. It's 1.5 as an exponent, so we don't consider that quadratic. Over here, looks like we're okay again. We have t squared, 2 is our highest power, but if we simplify this, t times t squared would be t to the third, so in fact this is a cubic. Let's look at some more characteristics of quadratic growth. So hopefully we know how to recognize a quadratic by looking at an equation now that we've learned the definition, but what about in a table? Well, you've been looking at tables of quadratics for a few days now, and hopefully you've noticed the pattern I'm about to show you. So let's look at this example of f of x equals x times x plus 1. Remember, this is a quadratic because we could simplify it using the distributive property, and we get f of x is equal to x squared plus x. And if we were to put in some x values, we'd get a table here. And let us remember that these are not the only x values we could choose. There's no restriction on the domain here, so we could really choose anything for our x values, but starting at 0 and going up is usually a good idea, not necessarily always, but let's see what happens if we do that here. So we plug in 0, we get 0 for f of x. F of 1 is 2, f of 2 is 6, etc. f of 6 is 42. And if we were to start to try to analyze this table and how this function is growing, we could look at the growth between the y values. We see from 0 to 2, it's going up plus 2. The function goes up 4 more, from 2 to 6. Then it goes up by 6. The function grows by 8, 10. Between 30 and 42, it grows by 12. So this definitely is not linear. You should know why it's not linear. And if we look more closely, though, we see that there is in fact a pattern here. It's not just randomly going up. It seems to be going up in an increasing fashion. In fact, from 2 to 4 is plus 2. From 4 to 6 is plus 2. From 6 to 8 is plus 2. So what we're seeing is that the growth here is actually growing by a constant amount. The growth isn't constant itself, but the growth is growing by a constant amount. So if this is the growth or the difference, and it's not constant, it's in fact increasing, we can call this over here the growth of the growth, or we can also call it the second difference. And the second difference here is constant, it's plus 2. So what makes something quadratic? Well, if the growth of the growth, also known as the second difference, is constant. It doesn't have to be plus 2, it could be plus 10, it could be 9, minus 6, minus 3, but it has to be a difference. In other words, it can't be times 2 or times 4. It has to be plus 2. So if it's a constant second difference, we have a quadratic. So think about, how is this different from a linear function? How is this different from an exponential function? We can also explore this growth by looking at the graph. So here, all we've done is we've graphed those same points that were in that table. So it's the same function, we graphed those points, but we talked about, well, how can we really see what's going on here? Is it a line? No, I don't think it's a line. Well, we could kind of connect the points in a way and see how is this function growing. And if we do that, we can see that it's actually looks like a curve. So we can connect these points with a curve. Well, this looks very similar to an exponential graph. So how do we know whether this is linear or exponential? Well, let's do a similar exploration as we did to the table. So as x increases by 1, y increased by 2 between 0 and 1. And then the next step, we went up by 4. Then it went up by 6. Then 8. Then 10. In fact, that's the same pattern that we saw on the table, which should come as no surprise. So here, again, we see that same pattern, 2, 4, 6, 8, 10. We see that there's a constant second difference of plus 2, because 2, 4, 6, 8, 10, those are increasing by 2. So again, we need to think, how is this different from a linear function? How is this different from an exponential function? It's obviously not a line, so it's not linear, but it does kind of look like an exponential. But when we look at that growth, we can see it is not exponential. There's no multiplying happening here. This isn't 2 times 2 is 4 times 2 is 8. No, that's not what's going on here. The second difference is just adding 2. But let's go back and think about what I said before. The domain here was never restricted, so this isn't even a complete picture of our graph. So far we have this over here, but what about negative values? Can we have negative numbers in our domain? Absolutely. Our domain was not restricted in any way. So if we put in the negatives, there they are over there. I also have a dashed line here, or a dashed curve. But that means that there are no points in between. Could we have points in between? Can we have non-integers in our domain? Could we have something at 1.5 right here? Something at 2.6 right here? Absolutely. Why not? Our domain was not restricted. So in fact, the graph should look more like this. A solid curve going through, showing our pattern here. So this point right here, even though there's a dot here, is not any more significant than this point over here that doesn't have a dot. They're both just points on this curve. So this shape here, this curve, it looks like a U, that's called a parabola. And quadratics always graph, the graph of a quadratic always looks like a parabola. We might not always see the whole parabola. We might only see part of the parabola. And if that's the case, it takes a little bit more effort to tell whether it is in fact a parabola or not, because we're only seeing part of it. So sometimes it can be confusing, especially between exponential and quadratic, if we don't see the whole parabola. So you really need to go back and think about this picture here. How are we growing? And if there is that second difference is constant, which means that the table is also going to show the second difference being constant, then we have quadratic growth. And we're always thinking, how is this different from a linear function? How is it different from an exponential function? So hopefully you have an idea now of how you can see whether a function is quadratic by looking at the equation, looking at the table, and looking at the graph.